Welcome to the deep dive. Today we're focusing on, well, the real workhorses of large-scale construction, steel trusses.
Absolutely. Think bridges, huge stadium roofs, those tall transmission towers.
Right, structures prized for that amazing strength-to-weight ratio.
Exactly. But the standard design approach, it makes a pretty big assumption.
Okay.
It assumes that under the design loads, every single piece stays perfectly elastic, springs back with no permanent deformation.
And that's where things get tricky in the real world, isn't it? Especially under extreme conditions.
If you're hit by a major earthquake or hurricane force winds, that elastic assumption, well, it doesn't tell the whole story. You need to know what happens after the steel starts yielding.
Because the purely elastic models, they miss crucial behaviors near collapse.
That's right. Two big things. Material yielding, that's the inelastic deformation piling up, and geometric nonlinearity.
Which is basically when things bend so much, the whole shape, the geometry, changes significantly.
Precisely. And that changes how the loads are carried.
Okay, so our mission today is to dive into a new, advanced design framework, one that's automated.
Yeah, it combines really sophisticated analysis, the finite element method, with a clever optimization tool, a genetic algorithm.
And the goal for you, listening, is to get inside the mechanics of this, how the physics and the math let engineers design structures that are much, much lighter.
Potentially huge material savings.
While still being absolutely safe, even when pushed right to the material's limits.
So let's start there. Why move beyond elasticity? For years, engineers saw stress over the yield point and, well, that was a fail, right? Design rejected.
Why wasn't that good enough?
Because it's often too conservative. It's potentially wasteful. Real structures can often handle significant load and absorb a lot of energy after yielding starts.
Through that plastic deformation.
Exactly. Stopping at the first sign of yielding doesn't reflect the actual collapse mechanism.
So plastic analysis becomes key. It lets us look beyond that initial elastic limit and assess those controlled inelastic deformations.
Right. It gives us a much better handle on the real collapse risk. We're not trying to avoid all deformation, just manage it safely.
Which brings us to that other piece you mentioned, geometric nonlinearity, those large displacements.
Yes, particularly in trusses with relatively slender members. If they bend a lot.
The original calculations about where the forces go are just wrong.
Pretty much. The whole structural response changes. You have to account for that deformed shape in the analysis. Otherwise, your predictions could be way off.
Like dangerously off.
Yeah.
Thinking it holds 10 tons, when really, after bending, it's only good for 5.
It can be that significant, yes. Now, this new framework, it builds on earlier work. People like Kaliski and Logo, they tackled plastic behavior.
But they had limitations.
They mostly assumed small displacements and, crucially, geometrically perfect structures.
Which never happens in reality. There are always tiny imperfections, right? From manufacturing, welding.
Exactly, those initial geometric imperfections. And this new approach, it handles the large deformations and lets you factor in those imperfections right from the start.
Why is that so important? Those tiny flaws.
Because they can be the trigger. They can cause the structure to buckle globally much sooner than a perfect model would predict. It's about realism.
Okay. So if we're allowing some yielding, intentionally letting the steel deform a bit plastically, how do we control it? How do we make sure it doesn't run away and lead to collapse? We need some kind of damage budget.
That's a good way to put it. The framework uses a specific measure for that. Complementary plastic work, or P dollars.
Okay, P dollars. Sounds technical. Give us the intuition. What is it measuring?
Think of it like accumulated plastic strain energy. When the material yields and deforms permanently, it dissipates energy. P dollars is a way to quantify the extent of that permanent inelastic deformation throughout the structure.
So it's a single number that captures how much yielding has happened overall.
Exactly. It's a scalar value, physically meaningful. And its role here is as a constraint. We set a maximum allowable limit, P-polar maxes.
So the optimization process can push the design towards lighter solutions, allowing some yielding, but only up to that P2MX budget.
Precisely. It keeps the plasticity within safe, predefined limits.
And to model that yielding accurately, you can't just use a simple on-off elastic plastic model.
No, you need more detail, especially if you're operating near the limits. This framework uses a quad linear steel model. It's based on work by Yun and Gardner.
Quad linear. 4 lines. Why 4 stages?
It captures the steel's stress-strain curve more realistically. You have the initial elastic part, then the yield plateau where strain increases a lot with little stress change.
Okay.
Then a strain hardening phase where it gets stronger again, and finally the region leading to ultimate failure.
I see. So if you're designing right up to that PD dollar limit, you really need to know exactly how the material behaves in that yield plateau and strain hardening zone. A simpler model might miss critical details.
Definitely. And that detailed material behavior needs to be plugged into the analysis that handles the large geometry changes.
Which uses the finite element method, FM.
Right. Using an incremental iterative approach. Basically, applying the load step by step and recalculating the structure's state at each step to find the equilibrium path.
And the overall physics framework, keeping it all consistent.
That's the total Lagrangian framework. It's crucial. It means all the calculations, stresses, strains, forces, are always referred back to the structure's original undeformed shape.
How is that important?
It prevents errors from accumulating as the structure deforms. It ensures the material laws and the geometric effects stay mathematically coupled and consistent no matter how much things bend or twist.
So it's tracking the whole journey, not just the end point, and keeping the physics straight all the way.
You got it. And that robust framework is also what makes it possible to properly include those initial geometric imperfections we talked about.
How are they modeled?
Typically as a combination of buckling, shapes the eigenmodes you get from a linear buckling analysis, or LBA.
So you figure out the most likely ways it could buckle.
And then you introduce a small imperfection in that shape into the starting model for the main analysis. It makes the simulation much more predictive of real-world behavior.
Okay, complex analysis engine sorted. Now, how do we use it to actually design something lighter? We need the optimizer.
Right. The core task is size optimization. We want to find the best cross-sectional area for each truss member to minimize the total structural weight.
But with maybe hundreds of members and all these complex nonlinear interactions between weight and safety, that's not simple math.
Not at all. Which is why the framework uses a genetic algorithm, or GA.
The evolutionary approach, inspired by natural selection.
Exactly. It works with a population of potential designs. It evaluates how fit each one is, meaning how light and how safe.
And then it uses genetic operators like selection, crossover, mutation to breed better designs over many generations.
That's the idea. It explores the design space very effectively to find near optimal solutions.
The key must be that fitness function. How does it judge a design? How does it balance weight versus safety?
It's cleverly designed. The main goal is minimize weight, yes, but then there are heavy penalty terms added if any safety constraints are violated.
Okay, let's break down those penalties. What's safety check number 1?
Load-bearing capacity. Can the design actually hold the target load, Ciro-Bermúdez, without collapsing? If it fails before reaching that load?
Big penalty. Design gets rejected by evolution.
Essentially, yes. It won't survive long in the GA population.
Penalty number 2 must relate to our plastic work budget.
You got it. The inelastic behavior penalty, $P penalty. If the calculated $P goes over the allowed limit, heavy penalty again. That enforces the controlled yielding idea.
Precisely. And the third major one is about overall stability.
Making sure it doesn't just buckle globally like a flimsy column.
Right. The global stability penalty. This uses the critical buckling factor, lambda, from that linear buckling analysis. If lambda is too low, usually below 1.0, indicates instability under the design load.
Penalty time. So the final design has to be stable. Absolutely. Load capacity, controlled plasticity, and global stability. They're all enforced through these penalties.
And I saw there's often an optional fourth check. A serviceability constraint. That's not strictly about collapse, is it?
No, it's more about performance and user comfort. A floor might be super strong, but if it bounces too much when you walk on it, or a roof sags visibly,
people won't like it, even if it's safe.
Exactly. So this constraint limits the maximum displacement, often using code rules like, say, the span length divided by $250 to $205 from Eurocode.
That's a really important distinction. Strength keeps it standing. Serviceability keeps people happy with it.
And importantly, adding that serviceability constraint often forces the design to be heavier. Stiffness costs material.
Let's see how that played out in the benchmarks. The source tested this on a couple of standard truss problems. First, the 37-bar planar truss. They compared 3 optimization runs.
Yes. E1 OP1 was purely elastic design. E1 OP2 was elasto-plastic, optimizing just for strength, allowing controlled yielding. And E1OP3 was elasto-plastic with that serviceability displacement constraint added.
And the results for material saving.
They were pretty striking. The winner for lightness was E1OP2, the strength-optimized elasto-plastic one. It cut the weight by an average of 55.7% compared to the starting design.
Wow, over half the weight removed, just by allowing controlled yielding.
That's what the analysis showed. Compare that to the purely elastic design, E1OP1, that only saved 48.5%.
So embracing plasticity bought an extra, 7% weight reduction? That's significant in real projects.
Huge. And we saw why. In the elastic design, the GA quickly learned to keep PP$ at zero, no yielding allowed.
But in the winning E1OP2,
the PP$ value hovered just below the PMX limit. The GA was actively using that plastic budget to squeeze out every bit of weight saving.
Okay, but what about adding the comfort factor? The stiffness constraint in E1OP3.
The weight saving dropped, down to 43.7%.
So forcing it to be stiffer definitely added weight back in. It confirms that trade-off.
Clearly, serviceability limits can cost you significantly in material compared to a pure strength optimization.
Let's look at the second test case, the 25-bar space truss. This one had an interesting starting point, didn't it?
It really did. The initial unoptimized design, it was actually unstable.
Unstable, even though it was probably quite heavy.
Yes. Its buckling factor, lambda, was only 0.388. Anything below 1.0 is bad news. It would have buckled long before reaching the target load. A classic example of a heavy but poorly configured structure.
So the optimization framework didn't just make it lighter. It fundamentally fixed a critical safety flaw.
Exactly. The optimized designs were stable, with a lambda well above 1.0. They carried the full load, and they reduced the weight compared to that flawed initial design by up to 19.1%.
Safer and lighter.
That's the goal.
Interestingly, on this space truss, adding the displacement constraint didn't seem to make much difference. The results for strength only, E2OP1, and strength plus stiffness, E2OP2, were almost the same.
Yeah, that was an interesting observation. It seems that for this particular geometry, the member sizes needed just to ensure global stability and strength already made the truss stiff enough to meet the L250 displacement limit.
So stiffness wasn't the driving constraint in that specific case?
Apparently not. Stability and strength requirements govern the design, and the serviceability limit was met automatically, more or less. It shows how the active constraint can change depending on the structure.
Okay, let's zoom out. What's the big picture here? We've got this framework using really advanced physics, nonlinear analysis, detailed material models, this PD dollar concept.
All integrated with a powerful optimization engine, the genetic algorithm.
And the result is automated design that can handle multiple complex safety criteria, simultaneously load, stability, controlled yielding,
while achieving potentially massive weight savings, like that 55% we saw. In the real world, that translates to lower costs, less material used, better sustainability.
It feels like a shift from just relying on big conservative safety factors in the elastic range
towards designing precisely for the required performance, even if that performance involves some controlled, well-understood inelastic behavior.
It's performance-based design pushed to a new level.
I think so. Designing for what it actually needs to do, using the material much more efficiently.
Which brings us to a final thought for you, our listener. This advanced approach demonstrates we can safely design structures that utilize controlled yielding to be incredibly efficient. So the question becomes, should we? Is the future of structural engineering moving away from simply preventing any yielding towards understanding and managing how a structure deforms right up to its safe limits? Could embracing controlled plasticity be key to building more sustainable and economical infrastructure?